Hello everybody, and welcome back to another Engineering Statics lecture video. As always, before we begin, I just want to say I hope you guys are doing well, because I'm about to change all that. I'm about to end your whole engineering career, if you will, by giving you guys depression in this video. Now, how am I going to do that? Well, I'm going to introduce one of the most hated topics, which is shear and bending moment diagrams. Now, this is where the true big brain time comes out, is in these diagrams here. As we talked about last lecture, beams have three internal forces, and we learned how to calculate these three internal forces at a single point. And I said, all right, well, that's great, but how do I know if that's my most critical point? Is that the location of maximum shear, maximum moment? Well, I don't know. And I said, get nice and comfy, because in the next video, we're going to discuss the idea of finding these internal forces at every point. And what we actually do is we create a diagram. So they're called shear and bending moment diagrams. Now, for some reason, I like to be a little bit dumb, and sometimes I'll say bending shear moment diagrams. Now, of course, shear moment diagrams makes no sense at all. So if I make that mistake, just know that I mean shear and bending moment diagrams. Now, I like to overplay this and make it sound difficult, but in reality, you guys are actually incredibly smart people. You guys are going to go through this and say, Clayton, piece of cake. And that's what I'm hoping for. If you guys can understand the content, well, that makes me happy as an instructor, because, well, that's why I'm here. That's my goal, to get you guys to understand the concept. So let's go through it together and let's see how well it sits with you guys. So let's begin. All right, so internal forces. Again, last lecture, we discussed the idea of beams and how they have three internal forces, that being the axial force, the shear force, and the bending moment. And then we took it a step further and we solved for these at very specific points. And we said, okay, that's great, but how do we know if that's the critical point? So what we're going to do now is we're going to learn to solve for these internal forces at every point throughout our beam. The reason why we do this is because this allows us to determine the critical shear and moment locations, which is important as a designer. As a designer, I don't care what the average shear is. What I care about is where the maximum shear is. And the same thing for moments. I care about where the maximum moment is and where it occurs, so I can design against it. So what we're basically going to do is we're going to take our beam, which I have pictured here, and we are going to create a diagram that looks something like this. So for this particular loading scenario, this is actually what our shear force diagram will look like. And this is the distribution of shear throughout our beam. As we can see, it is constant on the left side of that point load, and then it changes, but is still constant on the right side of that load. And we are going to do the exact same thing for what we call the bending moment diagram. So we are going to take our beam and we are going to figure out that actually our bending moment is going to look something like this. So again, this is the distribution of bending moment throughout our diagram. It looks a little bit complex, but as you guys are going to see, it's incredibly easy to do. Now, one thing that I really want to emphasize really quick before we begin is the way I'm going to show you in this video is kind of the shit way. It's not a good way of analyzing these diagrams. It turns out that there is a nice relationship between applied load, shear, and moment, and that's the topic of the next video. So this video, we are going to do kind of the brute force hard way of determining these diagrams, but the next video, I'm going to show you guys a nice little trick using the relationships between these to actually solve for these diagrams very fast and very quickly. So the method we learned today, I don't recommend it for exams. The method we learned in the next video, that's the way you guys are going to want to go. Now the question becomes, all right, Clayton, I see what you're trying to preach here. I understand what we're trying to do. How the hell do we do it? Well, to do this, we are going to utilize the same method that we did before, which involves cutting our beam and analyzing the internal forces. The only difference is before we would cut at a very specific point. And in this time, we're going to cut at an arbitrary location, which we're just going to call X. Now you guys may be saying, Clayton, what exactly does that mean? Well, don't worry. In the next slide, I'm going to show you. But before I do, I want you guys to notice one thing really quick. When we look at our diagrams above, we need a different cut each time there is a change in loading. So notice how for the shear force diagram, for example, I have two shear force functions. I got V1 and V2. And it depends whether I'm on the left side of that point load or the right side. So this is going to be one of the first things that we're going to have to start to realize is that whenever we have a change in loading, we're going to have a new shear force and bending moment function. All right, so that's kind of the first thing I want you guys to be aware of, and we're going to talk about this in the next slide. So let's start off simple. Let's talk about shear force diagrams. Now again, the way that we do this is the exact same way as before, but when we cut our beam, we're cutting it now at an arbitrary location rather than a specific location. So let's say that we have our beam here on the right, we have our dimensions, and I've already solved for the support conditions. Now notice that there's no horizontal load, so there is no horizontal reaction at that pin. I just have vertical reactions. Now what we're going to do is we are going to cut at an arbitrary location, and like we said in the previous slide, we're going to have to cut twice in this beam because the loading changes after that point load. So we're going to have to cut once on the left and once on the right. So let's start on the left hand side. So I'm going to go snip snip on my beam on the left hand side, and we are going to say that this is going to be segment 1. Now this segment 1 runs from x equals 0 all the way until x equals 3. So we're only concerned with everything on the left side of that point load. Well, after that, everything is actually pretty simple. We are going to draw the free body diagram just like we would if we were cutting at a specific point, but the differences start to occur once we talk about dimensions. So if we cut a beam, we know that we are going to have internal forces, which we see, but again, we're not cutting at a specific point. We're cutting at an arbitrary point. So what I would do is in this beam, I would label this dimension as simply x. Again, it's an arbitrary location. Now this is important because our normal force, shear force, and bending moments, they are now going to become functions of x. So when I'm labeling this diagram and I look at the axial force, I'm going to say N1 as a function of x. For the shear force, I'm going to say V1 as a function of x. And of course, for my bending moments, I'm going to have M1 as a function of x. Again, it's a function of x because we cut it at an arbitrary point, but we also have the ones there, M1, V1, and N1, because we know that we are actually going to have to analyze the second segment on the right side of that point load a little bit later on. So this is why I have it as V1, N1, and as well as M1. Now from here, it's actually rather simple. All we have to do is solve for these internal forces. And if we look here, we have 3 equations and 3 unknowns. So things are actually pretty simple. So if I were to go summation of forces in the x direction, I know that I have 2.5, which is my support reaction going upwards, and then I have minus V1 of x. Now, why is it negative? Because remember, beam internal forces always have a very specific sign convention, and that applies here too. We always have shear going downwards if we're analyzing the left-hand side. So if I were to look at this, I have 1 equation, only 1 unknown. I can say that my V1 of x is simply 2.5. Nice and simple. Notice that that x dimension actually didn't play any sort of role in this particular scenario. We're going to cover scenarios where it does play a role, but for this particular one, it didn't actually play a role. We found that V1 of x is simply 2.5. Now what I can do is I can take my free body diagram on the right hand side and I can begin to draw my shear force diagram underneath it. So what I'm going to do is I'm just going to extend dashed lines of all the locations of interest, and I'm going to start drawing my shear force along the length of the beam. Now V1 runs from x equals 0 all the way till x equals 3, and we know that our function is simply a constant 2.5. So in this diagram, I would simply have a nice constant line. We know its value is 2.5, and this is V1 of x. Now typically what students do to help really show what's going on is we also kind of shade in this region. So for my first segment here, this is how I would find my shear force. It's actually nice and simple. It sounds like it's going to be some crazy shit, but it turns out to be pretty simple, which is good for us. We want simple. That's kind of what we go for. Now again, whenever we have a change of loading, we have to again analyze the segment after. So after we have that point load, we actually have to cut the beam a second time to analyze this second segment, if you will. So I'm going to go segment 2, and this segment is valid from x equals 3 all the way until x equals 4. How do I analyze it? Well, it's going to be the same thing as before, where I'm going to draw my free body diagram. And again, we have to make it as a function of x, an arbitrary location. So what I'm going to do is I'm going to say I have my internal forces, same thing as before, where it's going to be V2 of x, N2 of x, and M2 of x. And they are going to be at an arbitrary location, x. Now, one other dimension that we do know and we have to include is we know that our point load of 10 is located at a distance of 3 from the left support. So this would be another dimension that I want to include in this free body diagram. Now, if I were to go here and go with summation of forces in the y direction, it's actually quite simple. We have 2.5 going upwards, so plus 2.5. We have a point load of 10 going downwards, so minus 10. And then we have our shear force also going downwards, so minus V2. From here, one equation, one unknown, we can actually figure out that V2 is equal to negative 7.5. Now what would I do is I would take this and I would go to my shear force diagram and say that for this second segment, we know that our shear force is negative 7.5 and it doesn't change, it's constant. So I would draw my nice line, and then if I want to, I would shade it in. Now, as we can see here, we now have a complete diagram showing the distribution of shear force along my beam. Now this is very important because as a designer, I now know that the maximum location of shear is going to be in that second segment, and the magnitude is negative 7.5. So all I would do is I'd go to my beam catalog, I would find a beam that's capable of handling that 7.5, I'm good to go. So this is why these diagrams are so important. The last thing that I really want to emphasize to you guys is the idea that for this particular example, we needed 2 cuts. Every time there is a loading change, it actually creates a discontinuity in our shear force. As we can see, we started off positive, but that point load actually caused a discontinuity in our diagram. Therefore, we actually needed 2 cuts. Now, I also want to kind of, I don't know, tease you guys for the next video. Tease you guys. It sounds very sexual. I'm nothing sexual. I'm just trying to get you guys excited for the next video. If I wanted to, and again, we're going to cover this a lot in the next video, I could have figured this out in 3 seconds. And the reason why is this. Notice that our shear force in segment 1 is 2.5. And notice how our support reaction is also 2.5. So if I wanted to, I could have started off at the very left, simply went up 2.5, and in the first segment, nothing happens. So I could have just carried that 2.5 along. Now notice that at x equals 3, there's a downward load of 10. So if I were to take 2.5 and subtract 10, well then I go down to 7.5, or negative 7.5, which is what we had. And then in segment 2 there, again, nothing happens. So I could have carried that negative 7.5 along. And then notice at the very end of the beam, we have a support reaction up, a 7.5. So negative 7.5 plus 7.5, I go back to 0. So this is one of the relationships that we're going to use next video to very quickly create these diagrams, which is important. Remember, in exam type scenarios, you guys always want to be fast, right? That's a lot faster than cutting the beam twice, doing 2 free body diagrams, equilibrium, etc. It's better to just use relationships. And again, we're going to talk about those a lot in the next video. So that's shear force. What about bending moment? Well, bending moment is actually going to be the exact same procedure as shear force. We are going to use even the exact same free body diagram. So the only difference is rather than summation of the forces in the y direction, we are going to do this summation of moments to solve for that m1 of x or m2 of x. So if we go back to the same beam here, we know that for our very first scenario, we're interested in this first segment between x equals 0 and x equals 3. I'm going to have the same free body diagram as I did before. And remember, this is going to be a function of an arbitrary location x. Now, instead of taking the summation of forces in the y direction to solve for v1, I'm going to take the summation of moments about the cut. Again, I always like to take it about the cut. It usually leads to less errors. So if I were to take the summation of moments about the cuts, I have 2 things that play a role. First is going to be m1 of x. That's kind of easy. You guys can see that. The second one we know is that support reaction is going to create a moment. And if I were to analyze it at the cut, so this point's at the cuts, my support reaction is going upwards, we see that it's going to create a clockwise moment, so it's going to be negative, and it's going to be force times distance. So we're going to have the 2.5, but notice that the distance between the cut and the support reaction is simply x. So we're going to have negative 2.5 times x. So if I were to solve for m1 of x, we get that m1 of x is actually equal to 2.5x. It's now a function of x. It's a linear function. So if I were to go over to my moment diagram, which I would actually draw underneath my shear diagram, I would say that this equation would actually have a line of something like this. If I were to substitute x equals 3, 2.5 times 3, I get 7.5. So again, just like before, I would also shade this in, and I would say that this is my initial region. This is my moment distribution for that first segment. Now, if I want the second segment, I'm going to do the same procedure. So instead of cutting in segment 1, I'm going to move my cut over to segment 2, and I'm going to analyze it where x is between 3 and 4. Again, I'm going to have the same free body diagram as before. So this is a nice thing. If you're solving for both the shear force diagram and the bending moment diagram, you could have done them both at once. You don't have to keep drawing diagrams over and over again because they're going to be the same. I can take the summation of moment about the cut, and then I get this equation right here. Now again, 2.5 times the distance x, and then the point load acts at a distance of x minus 3. X all the way to the load, and then we have to subtract that 3 part. Therefore, I get m2 of x is equal to 2.5x minus 10 multiplied by x minus 3. If I were to substitute x equals 3 into this equation, I get 7.5. And if I were to substitute 4 into this equation, I actually get 0. So my line is going to look something like this. And then, of course, I would shade it in. So there's a couple things I want to mention here really quick. As we've seen in shear diagrams, and now we're also seeing in moment diagrams, they always end and start at 0. The end of the beam and both ends of the beam are going to start at 0. Of course, the support reactions will pop it up, but they always end at 0. If we had a concentrated moment, like a fixed support, that'll also pop it up, but they should always start and end at 0. There's the first thing. The second thing that we can see is we now have a linear profile. So that's one thing that we didn't see in the shear force case. That function of x, it didn't really play a role. We had constant shear in our segments. Now we can see that our moment profile in our segments is actually linear. And this is, again, great because if I were to look at this profile, I now know that the maximum moment is going to be 7.5, and it occurs at a location of x minus 3. So this is the power of these diagrams. They show us the complete shear and moment distribution throughout our diagrams. It's very nice for us. Now, we're going to talk about something that I've kind of mentioned a lot, which is continuity. Now, as I said, every time there is a change in load, there creates a discontinuity in our beam. For shear, when we had that point load, we had to drop it. And in the moment diagram, we are originally going up, but because of that point load, we actually changed course and started coming down. Now, these discontinuities occur in 3 different ways. The first one is a change in load pattern. So if I had nothing on my beam and then suddenly I had a distributed load, that's actually a change in load pattern. So this would create a discontinuity. The second one is a concentrated load or moment. And again, we saw this in the previous slides. When we had that point load, it would create a sudden jump in our shear force diagram. And then the final one, which actually goes back to point 2, is a support reaction. Because remember, support reactions create those point loads, and whenever we have a point load, we have to jump up or down when it comes to shear. Now, what I like to do to try and analyze these sections is every time I see one of these discontinuities, I like to draw a line. And this will kind of tell me what segments I need to analyze. So let's look at this beam right here. Quite a complex beam. We have 2 different distributed loads. We have a point load and we have support reactions. So the first thing I like to do is, of course, show my support reactions as point loads. Therefore, we can apply kind of case number 2 to these. And then what I'm going to do is I'm just going to go from the left all the way to the right side of my beam and analyze when there is a change in load or a concentrated load. So you can see right at the beginning we have a Y, which is a point load, so I would simply create a line. Now moving forward, nothing happens in my beam, but then suddenly there is now a distributed load. That's a change in loading, so I would create another line right there. From there I'd keep going forward and my distributed load stays the same, so nothing happens. But then I have a point load P suddenly, so I'd create another line right there. From there, the distributed load stays the same, nothing happens, but then the distributed load ends. So this would be another line. From here, nothing happens on my beam. Oh, and then suddenly I have a support reaction. So this would be another line. Again, nothing happens, distributed load, another line. And then at the very end, my distributed load ends, I would have another line. Now, why did I draw these lines? Well, these show me every section I actually have to cut to create my full shear force and bending moment diagram. I'd have section 1, section 2, section 3, section 4, 5, and 6. So if I wanted a complete shear force diagram and bending moment diagram of this beam, I would need to cut it 6 times. 6 times. That's crazy. If you guys are in your final exam and you guys are cutting a beam 6 times, you're not finishing that exam. That's the Clayton guarantee. I guarantee no one's finishing their exam. So this goes back to what I was saying previously, is that there's actually very nice relationships between load, shear, and moment that will actually allow us to solve for these diagrams very fast. Using these relationships, we can actually take this beam that we just saw and said it's mega ass, but we can actually solve for it very, very fast. So again, if that's what you guys want, that's the topic of the next video. Now, before we get into that, I just want to give you guys a general procedure for determining these shear forces and bending moment diagrams using this cutting method, if you will. It's actually a very simple procedure. So let's say that we have our beam and we now have a distributed load of 5 and our beam is 2 meters or 2 feet long. Well, the procedure is going to look something like this. First, we want to draw the entire free body diagram of the entire member. So no cutting, just the entire member, and we get something like this. Now there's no horizontal load, so I didn't include the horizontal reaction force. So you guys have to kind of forgive me there, but it's going to mainly look like this. From here, we can solve for our reaction forces using our equilibrium equations. So if this was my loading case, I would find out that both of my reaction forces are actually equal to 5. So these would be 5 kilonewtons, 5 pounds, whatever you guys want your units of force to be. So this is the easy part and something that we've done a long time. This should be nothing new. Where it starts to get new is this. We are now going to cut our beam at the region of interest. Now we're actually lucky because this beam, there's only one region. There's no sudden loading change anywhere. The previous beam, remember, we had 6. So we'd have to cut it 6 times. Here we just cut it once, so I can pick any location and just simply go snip, snip. From here, I'm going to take that region that I just cut and I'm going to create a free body diagram of it. But again, the key here is I'm going to make the length of that free body diagram that variable length x. So if this was my free body diagram after the cut, I'm going to say that this distance here is x. Now, of course, when we cut our beam, we have those internal forces. So we're going to have Vx, Nx, as well as Mx. Notice how we're not actually too concerned with our axial force Nx. It's mainly just Vx and Mx, or shear and bending moments, that we're concerned with. From here, we can solve for Vx and Mx using our equilibrium equations. So for instance, we know that if we wanted our shear, we can take the summation of forces in the y direction. I would have 5 coming up from my support reaction, and then I would have 5 times x going downwards, which is my distributed load, and then minus my shear, and that's of course going to be equal to 0. Now notice in the first example that we had where we just had a point load, that variable length x didn't play any sort of role. Both of our shear functions were constant. But now we can see that if we have a distributed load, the magnitude of that distributed load is a function of the area of it. So of course the height is going to be 5, but the length is going to be x. So now if we were to solve for v of x, we see that it is now a function of x. We have 5 minus 5x. This is going to be our shear force function. If I wanted my bending moment, I can do the summation of moments about the cut, and I get negative 5 times x plus 5x times x over 2 plus mx is equal to 0. Now again, it becomes a little bit tricky when we start dealing with these distributed loads. 5 times x, remember, that is the magnitude of this distributed load. And then I have to take that magnitude and I have to multiply it by its distance to the cut. So remember that rectangles for distributed loads, the point load acts right in the center. So if the whole rectangle is x, well then the point load is going to act at x over 2. So that's where it comes from. 5 times x is the magnitude, x over 2, that is the distance. Just really want to clarify that for you guys. And once we do that, we get 5x minus 2.5 x squared. So in this case, instead of linear, we now have a parabolic function. Excuse me. All right. So what we would do then, if we had multiple segments like we did in the previous example, we would repeat steps 3 through 4. We would then move on to the next section, make our cut, find our functions, then move on to the next section, make our cut, find our functions. Here it's kind of lucky because we just have that one section, so we don't really need step 6 in this case. Now step 7 is where it's going to get fun. As a professor, this is what I'm going to look at when I'm marking your exams, is step 7, where once we have our functions, we actually need to draw a complete shear force diagram and bending moment diagram underneath the free body diagram. So if this was my free body diagram, I would simply draw my shear force diagram line and my bending moment line underneath it, and then I would use my functions to actually draw the distribution. So remember, for shear, we had our function as 5 minus 5x. So if I were to plot this over the length, I know my function is going to go from 5 all the way down to -5. Now again, if we look at the support reactions, it's kind of funny, isn't it? I start by going up 5, then I go downwards, and I'm at -5, but then my support reaction is +5, I end back up at 0. So it's one of those fun things. And again, we like to shade it in just to make it look pretty. I know as engineers we're not very artistic, but we try our best. Now that's going to be shear force. Moving on to bending moment, it's no problem. We have our nice equation, 5x minus 2.5x squared. This is actually going to be a parabolic distribution. Now this is where the fun comes in. And this is where I really want you guys to start thinking of relationships. I've already talked about how the support reactions kind of pop or shear force up and pop it down, whatever. But notice this. Our line is linear, and the slope of this line is -5. Notice that our distributed load has a magnitude of 5. The slope is -5, distributed load has a slope of 5, or a magnitude of 5. As we're going to find out, the magnitude of our distributed load, that is the slope of our shear force diagram. And we can take this a step further. If we look at our shear force equation and our bending moment equation, there's a nice relationship. If I were to take my shear force and integrate it, well, I would get 5x minus 5 over 2x squared. 5 over 2, well, that's 2.5. If I look at my bending moment equation, that's the same thing. So one of the things we're going to realize is our shear force is actually the derivative of our bending moment. All right, so that's kind of the fun little things that we are going to explore later on. Now, if that's the case, and our shear force is the derivative, and we were to take that derivative and set it equal to 0, well, we know that's how we find minimums or maximums. So if we were to look at our shear force and locate the point where it's equal to 0, notice how that's the location of the maximum bending moment. So as we're going to discuss next video, everything here is intertwined. And this allows us to very, very quickly solve for these diagrams without having to do any sort of equilibrium, without having to draw a bunch of free body diagrams. If I wanted to, I could have just went right to this step and showed you guys the diagrams. It's actually really nice and easy, which we are going to again discuss in the next video. So if you guys are looking at this and saying, Clayton, this is garbage, this is hot garbage, don't worry. Next video, we're going to discuss a more simple way of doing this very quickly. And that's it for this video. So again, just like to remind you guys in the occasional video too, if this is a bit complex, don't worry. It always is for first years. Go down to the description below. I will include an example or two on how to solve these diagrams using this cutting method. And for the next video, I will have examples on how to show you guys how to solve them using relationships. So again, best way to solve these or actually understand the concepts is through examples. I will have plenty of examples for you guys. I promise you, by the end, you guys will understand this, or at least that's what I'm hoping for. All right, but yeah, that's it for this video. I'm sorry, I know it's a long one. This concept is rather stinky, where it requires a lot of effort, a lot of intuition on how to do it. But again, you guys are very smart. I trust every single one of you. You guys are probably laughing at me, saying, Clayton, this is too easy. Give me something harder. And to that, I say, don't worry, friction is coming up, and that'll piss everyone off. All right, guys, you guys have a wonderful day, and I will see you guys in the next lecture video.